Hello, this is Dr. Hanaa Assil, and this is chemical equilibrium. This is for IA2 chemistry at Edexcel, but it could apply to any other syllabus. So let's talk about chemical equilibrium. This has to do with reversible reactions, and you should know that reversible reactions are reactions that go both forward and backward without going to completion. So if we have reactants, they react and form products. The products break down and form reactants. This is a reversible reaction. Usually in a normal complete reaction, the reactants would just form products and that's it. But if the products break down and form reactants and then the reactants again form products, then this is a reversible reaction. For example, the Haber process, nitrogen plus hydrogen to give ammonia, is a reversible reaction in which nitrogen and hydrogen will react to form ammonia, but then some of the ammonia will break down and form nitrogen and hydrogen again, and this goes forward and backward until we reach what? Until we reach dynamic equilibrium. Now, when the reaction is in dynamic equilibrium, this means that we have reached a state in which the rate of the forward reaction equals the rate of the backward reaction, and concentrations of reactants and products remain constant. For example, if we have NO2 gas, which is brown, it will form N2O4 gas, which is colorless, and then the colorless gas will form the NO2 brown gas again. But at dynamic equilibrium, they are somewhere in between, in which the concentrations of the NO2 and the N2O4 are constant. So this is dynamic equilibrium. Let's take a look at this question. It says a substance X forms a new substance Y in an equilibrium reaction X giving Y. In an experiment, X and Y are mixed and react, reaching equilibrium at time t. Can you see where time t is on the graphs? Which diagram represents the variation in concentrations of X and Y with time? Now, we are starting with X, so the value for X should be very high. And then it forms Y. So Y at the beginning is very low, but then it increases. And then he's saying, in an experiment, X and Y are mixed and react, reaching equilibrium at time t, which diagram represents the variation in concentration. So at time t, what is happening to the concentrations of X? X should be high and then decrease. Y should be low and then increase. And that means the graph representing this equilibrium state is graph D. We have something called Le Chatelier's principle, and you probably heard about this before. It says if a system is in dynamic equilibrium and then it is subjected to a change, the position of equilibrium will shift in the direction that reduces the change. So if we have dynamic equilibrium, means A plus B to give C plus D should be balanced. If we do anything to distort this balance, the reaction will try to do something in the opposite direction in order to reduce the effect of the change that we did. So let's take a look at what this means. If I change conditions of a reaction, for example, I have the Haber process, nitrogen plus hydrogen to give ammonia, and we know that the forward reaction here is an exothermic reaction since delta H is negative. That means that as the nitrogen and hydrogen form ammonia, the reaction becomes hotter. If it goes back and the ammonia breaks up, that is an endothermic reaction, so the reaction becomes colder. Now, if I want to force the reaction to go forward or backward, I can change the conditions. Which conditions can we change? We can change the concentrations. That means add more nitrogen and hydrogen or add more ammonia, change the temperature, lower it or increase it, change the pressure since we are dealing with gases. Remember that pressure applies only if the equation involves gases. So let's take a look at the effect of each change. So if we're changing pressure, what happens to an equilibrium reaction like this? Now, you should realize that if we increase the pressure, that means the volume decreases, you're pressing the particles nearer to each other. It doesn't like that. It will try to go to the side that will relieve this pressure. That means when we increase the pressure, it will go to the side that will form less number of moles. So if we look at this equation, if I go forward, I form 2 moles of ammonia. If I go backward, I will form 1 mole of nitrogen plus 3 moles of hydrogen, that's 4 moles. So if we increase the pressure on this reaction, where will it go? It will go to the side with less number of moles. That means it will favor the forward reaction, or the point of equilibrium will shift to the right, and that would form more ammonia. So if he's saying we're increasing pressure, what is the effect on the point of equilibrium? It will shift to the right, or it will go forward. What is the effect on the yield of ammonia? It gives more ammonia since it is going forward and forming more and more of the ammonia. What if we change temperature? Now, what happens if I increase the temperature of a reversible reaction? Well, this reaction, for example, Hi to give H2 plus I2, is an endothermic reaction. That means as it goes forward, it becomes colder. Now, if we increase the temperature, it will try to cool itself down. So it will try to go forward. So in this reaction, increasing the temperature favors the endothermic side so that we can use up the excess heat. So increasing the temperature in this case will shift the equilibrium to the right or cause the reaction to go forward. What if we do the same to this? Now this is an exothermic reaction. If I increase the temperature, that means I'm making it hotter. It will try to cool itself. So it will go backward. So it will form less ammonia. So if the reaction is exo, increasing the temperature causes it to go backward, less yield of the product. What about if I add a catalyst? Well, we know that a catalyst speeds up a reaction. For a reversible reaction, it speeds up both forward and backward reactions. So actually, it would have no effect on the point of equilibrium. It will not favor forward or backward. It will speed up both forward and backward, and that means we will reach equilibrium faster, but it will not favor forward or backward. What if we change concentration? Well, what are we doing? If we add more reactants, that means I'm adding more nitrogen or more hydrogen. It will try to go forward to use up these added amounts because it wants to return back to the original amount of reactants and products. So adding reactants causes any reversible reaction to go forward. Removing the products or removing the ammonia will also cause it to go forward. Now, if I add more ammonia, adding more ammonia means it will go backward in order to use up this extra amount of ammonia. So remember, adding more reactants causes the reaction to go forward. Adding more products causes the reaction to go back. So let's take a look at this question. He says the Oswald process is a method for making nitric acid. The equation for the first stage of this process is this. Notice that it is an exothermic reaction. Which of the following would both decrease the equilibrium yield of nitrogen monoxide? So NO, I want to decrease NO. So in order to decrease NO, that means I want the reaction to go backward. So which of these will cause the reaction to go backward? Well, Looking at the reaction, the delta H is negative, so the forward is exo. So if I wanted to go backward, remember I need to increase the temperature because backward is endo. I increase the temperature, it goes endothermic. So with respect to temperature, I want to increase it. What about pressure? I want the reaction to go backward. That means it will go to the side that will give less moles or more moles. It is going from 4NO plus 6H2O going backward to 4NH3 plus 5O2. So I'm forming, instead of 10, I'm forming 9. So I'm decreasing the number of moles. We said in order to go to the side with less number of moles, we need to do what to the pressure? We need to increase the pressure. So actually, to go backward in this reaction, I need to increase both pressure and temperature. What about this question? The graph shows the variation with temperature of percentage yield of product in a gaseous equilibrium at different pressures. So he has the graph for 200 atm and he has the graph for 150 atm. So is the forward reaction positive delta H or negative delta H? Well, let us see. If we increase the temperature, do we get more product or less product? As we increase the temperature going to the right in the graph, the product is increasing. That means increasing the temperature goes forward. We said increasing the temperature goes endo. So the forward is endo, so the delta H is positive. Now, what about pressure? What is happening when we increase the pressure? Well, from the graph, the 200 atm gives me less product than the 150 atm. That means increasing the pressure goes backward. And that means that the forward reaction has more moles because we said increasing the pressure goes to the side with less moles. So if increasing the pressure goes backward, that is the side that has less moles. That means the forward reaction, the number of moles is more or it increases. Are we following? Okay, this is another reversible reaction, and he's saying the addition of a small quantity of sodium hydroxide to an orange equilibrium mixture would do what? Now, remember, we're adding sodium hydroxide. What does that have to do with my equation? If I add sodium hydroxide, what it is doing is it is reacting with the H plus ions. So it is as if I am removing the H plus ion. Sodium hydroxide is a base. It will react with the acid. So it removes the H plus from the reaction, and that means this forces the reaction to go forward, and that means the reaction should change from orange to yellow, or it should go to the right. Now, which statement says that? It shifts the equilibrium position to the right. Remember, it doesn't change from orange to green or orange to colorless. No. If we're talking orange to what? It should be orange to yellow, or it should shift to the right or go forward. Okay. Another reaction is the cracking of alkanes, and he has the equation, and he says when the pressure is increased, the reaction shifts to which side? Well, if I increase pressure, it goes to the side with less number of moles. So it goes to the left or backward to re-establish the equilibrium. Then we need to know how to write equilibrium constants. So if I have any reversible reaction with its coefficients, so I have reactant A with a certain coefficient plus reactant B with a certain coefficient to give product C and D with certain coefficients, an equilibrium constant is an expression of the concentrations or the pressures raised to their coefficients. We have products over reactants. So we have C to the coefficient of C plus times D with the coefficient of D over the reactants raised to their coefficients. Remember that the Kc, we call it the equilibrium constant. So it's a certain value for the concentrations of products over reactants. Remember, when we indicate concentration of something, we need to put it in a square bracket. It cannot be in a round bracket. It has to be in a square bracket to indicate concentration, and the units of concentration are usually mole per decimeter cubed. I can also express this with respect to pressure. So Kp is the equilibrium constant with respect to pressure. It has to do with the partial pressures of each one. Now, this has to apply to a reaction that has only gases, and the partial pressure of each gas is relative to the amount of pressure it exerts in the mixture. So Kp in this case is the equilibrium constant for the reaction in pressure. The P's of each one is the partial pressure of the gas. So it is the pressure exerted by the gas in the mixture. And if we want to calculate it, we calculate it with respect to the number of moles. So the partial pressure of one of these gases is relative to the number of moles. So it will be the number of moles of that gas over the total number of moles times the total pressure. This will give me the partial pressure of each gas. So if I have this equation, how do we write the expression for Kc or Kp? Now, Kc is concentration of ammonia to the power 2 divided by concentration of nitrogen to the power 1 times concentration of hydrogen to the power 3. If I write Kp, and I can do that because all of these are gases, it is the partial pressure of ammonia to the power 2 over the partial pressure of nitrogen times the partial pressure of hydrogen to the power 3. For this equation, let's write the Kc and the Kp. Can you see how we did that? Concentrations have to be square brackets of Hi to the power 2 over, remember, it is products over reactants, each to the power of its coefficient. If we're talking about Kp, it is the partial pressure of each raised to its coefficient. So let's take a look at some questions. The equilibrium involving phosphorus pentachloride in equilibrium with PCl3 and chlorine gas. And he gives me the value of Kp is 1.8. So first of all, he's asking what is the expression for the partial pressure of chlorine gas. We said, how do we get the partial pressure of one of them? The partial pressure of one of them is its number of moles over the total number of moles times the total pressure. So which of these expressions is the same as that? It is that first one, the total pressure times moles of chlorine gas divided by total moles of gas. What are the units? How do we get units of the equilibrium constants? Well, let's take a look at this. Now, Kp is, for this reaction, I want to write the expression for Kp. Kp is partial pressure of R to the power 8 over partial pressure of P times partial pressure of Q to the power 3. Now, what are the units for each of these? Remember that pressure is in atmospheres. So if we say partial pressure of R to the power 8, that means the unit is atmosphere to the power 8. Over, I have atmosphere times atmosphere to the power 3, so that's atmosphere to the power 4, and that means that the total is atmosphere to the power 4. So that is the unit for Kp for this reaction. Remember, the units for Kc and Kp differ from one reaction to the next. Notice that equilibrium constants at a certain temperature are independent of concentration or pressure. So changing concentration does not change Kc. Changing pressure does not change Kp. The equilibrium constants will change only if you change temperature. Equilibrium constants will differ from one temperature to another. We said catalysts cause equilibrium to be reached more quickly, but they have no effect on point of equilibrium, and they have no effect on the value of equilibrium constant. So always remember, the only thing that will change equilibrium constant if we change temperature. So let's take a look at this question. It says the Haber process is used to make ammonia from nitrogen and hydrogen, and he has the equation, and we said the forward reaction is exothermic. When the reaction of the system is increased, now he's going to increase temperature. What happens to Kp? Remember, the value for Kp is the partial pressure of ammonia raised to the power 2 over the partial pressure of nitrogen times the partial pressure of hydrogen to the power 3. Now he's saying the temperature is increased. If the temperature is increased, that means the reaction will go backward, because the forward is exo, so the backward is endo, and we said when temperature is increased, the reaction goes endo. Endo means we will have less product, so the partial pressure of ammonia will be less, and that means that the Kp will decrease since the numerator in the equation is lower. Another question, the reaction shown is at equilibrium. The forward reaction is endothermic. And he gives the equation and he says which will increase when the temperature is lowered. So he's saying the forward reaction is endothermic. And that means if I lower the temperature, we said what happens if I lower the temperature? We said if I increase the temperature, it goes endo. So if I increase, it will go forward here. But I'm decreasing the temperature, so it goes backward. So what will increase? If it goes backward, it gives more what? It gives more carbon dioxide. So the mole fraction of carbon dioxide will. Now, what about the other choices? He says the partial pressure of carbon monoxide. No, the partial pressure of carbon monoxide would decrease, not increase. The rate of the backward reaction. No, remember, if I lower the temperature, the rate will decrease, not increase. The value of Kp, well, if we look at this and I'm going backward, Kp is pressure of CO over to the power 2 over pressure of CO2. The value for Kp for the forward reaction would actually decrease because the amount of CO, or the partial pressure of CO, is lower. So my answer here is A. Magnitude of equilibrium constant determines the extent to which any particular reaction can proceed under given conditions. So if I have a certain reaction, and this is the expression for my Kc. Now, if the value for Kc is high, that means I have a lot of CND. And that means that the forward reaction is fast. So a small value of Kp or Kc would indicate that the reaction takes place only to a small extent, because I will have only a small amount of CND and the concentration of the products is very small, so the Kp or Kc would be small. So the magnitude of the K equilibrium constant determines whether the reaction is going forward or back. So let's take a look at this question. Water and tetrachloromethane are immiscible liquids. When an aqueous solution of iodine is shaken with an equal volume of tetrachloromethane, an equilibrium is established. So I have this equilibrium between iodine in water, aqueous, or iodine in carbon tetrachloride. Now, the data on this equilibrium system says the Kc is 86.0. What does that tell you? If the Kc is 86.0, and Kc, you know, is the concentration of iodine in carbon tetrachloride over the concentration of iodine in water, that means I have more iodine in the carbon tetrachloride than in water. And then when he says densities of water and the carbon tetrachloride, and the density of carbon tetrachloride is more than water, that means I have two layers in which the carbon tetrachloride is the tetrachloromethane is the lower layer, water has lower density, so it will be above it, and the iodine is more soluble in the carbon tetrachloride, so at equilibrium, water will be the upper layer and will have a smaller concentration of iodine. Consider the reaction. How are Kp and the mole fraction of PCl5 affected when the pressure is increased? First of all, we said if we increase pressure, what effect does that have on the value for Kp? Nothing. We said it will not affect, so the Kp actually should remain unchanged. What about the mole fraction of PCl5? Well, let's see. When pressure is increased, will the reaction go forward or backward? It will go forward because we said increasing the pressure, the reaction goes to the side with less number of moles. So it will go forward to form 1 mole of PCl5 instead of 1 mole of PCl3 and 1 mole of Cl2. So when the reaction goes forward, then the mole fraction of PCl5 would increase. Equal amounts of W and X are mixed and allowed to reach equilibrium. The value of the equilibrium constant is 4.85. So at equilibrium, the mixture will contain what? You know that the Kc is concentration of Y times concentration of Z over concentration of W times concentration of X, concentration of products over reactants. So if he says that Kc is 4.85, that means that I have a lot of Y and Z. And that means at equilibrium, we have all of them, W, X, Y, and Z, but there is more Y and Z than W and X, so that makes my Kc a large number. Are we following all of this? Under different conditions, he says 25% of the moles of gas present at equilibrium is N2O4. If the total pressure of the system is 3 atm, what is the numerical value of the equilibrium constant Kp? Well, let us see. He's saying that I have Kp should be the partial pressure of NO2 to the power 2 over the partial pressure of N2O4. And then he says at equilibrium, what happens? We have 25% of the moles are N2O4. So that means the partial pressure of N2O4 is 25 over 100 times the total, which is 3. So the partial pressure of N2O4 is 0.75. The partial pressure of NO2 is the rest of the 3. So you can either say 3 times 75 over 100 or just 3 minus 0.75. So that comes out to be 2.25. And that means that my value for Kp is, we said, the partial pressure of the NO2 to the power 2 over the partial pressure of N2O4. And that comes out to be 6.75. Okay, let's take a look at this question. Nitrogen reacts with hydrogen to form ammonia. The units for the equilibrium constant Kc are what? We said in order to get the units, we write the expression for Kc, concentration of ammonia to the power 2 over concentration of nitrogen times concentration of hydrogen to the power 3. And then you write the units. Remember that each of these concentrations is mole per decimeter cube. So if I have concentration of ammonia to the power 2, it's moles to the power 2, decimeter to the power 6. Then I have nitrogen is mole per decimeter cubed. Hydrogen is mole to the power 3 per decimeter cubed, which is to the power 3, so that's decimeter cubed 9. If you cancel the same up and down, you end up with this unit, decimeter to the power 6, mole to the power minus 2. The highest equilibrium yield of ammonia is produced at what? Okay, what would cause a lot of ammonia to be formed? First of all, with respect to temperature, do I want high temperature or low temperature? Remember that the forward is exo. In order to go forward, I need low temperature because we said increasing temperature goes endo. So decreasing the temperature would go exo. So I need to lower the temperature. What about pressure? I need pressure to be higher or lower, I need to go forward. Forward will give 2 moles, while backward will give 4. So to give less number of moles, I need high pressure. So that is low temperature and high pressure would favor the forward reaction. This reaction has a numerical value of Kp 1.8, and he says the equilibrium partial pressures of phosphorus chloride and chlorine gas are this. What is the equilibrium partial pressure of PCl5? So let's take a look at this. He's saying we have Kp, expression for Kp would be partial pressure of Cl2 times the partial pressure of PCl3 over the partial pressure of PCl5. And he's given me the value is 1.8. Now I can use that, put in the values for the partial pressure of chlorine, which he gives 0.946. Partial pressure for PCl3 is 0.614 over the partial pressure of what we're trying to get, and just straight mathematics will give 0.32. Okay, the reaction between hydrogen and iodine may be represented by two equations. For equation 1, the equilibrium constant, we're going to call it Kp1. For equation 2, the equilibrium constant is Kp2. What is the relationship between Kp1 and Kp2? Remember that equilibrium constant expression depends on the equation. So if I write the Kp for the first equation would be this, the Kp for the second equation would be this. So what is the relationship between them? One has Hi to the power 2 over H2 times I2. The other one has Hi to the power 1 over hydrogen to the power half, and so on. So this, from this, the Kp for the equation 1 will be equal to the Kp for equation 2 to the power 2. So if you do that last equation to the power 2, you get Kp1. So that is the relationship. So remember that Kp depends on chemical equation. For this question, he says the reversible reaction between hydrogen chloride and oxygen produces water vapor and chlorine. Explain what effect, if any, each of the following changes has on the yield of chlorine and the equilibrium constant Kp. So he has this equation. He says, okay, what are we doing? We're going to increase pressure. What effect would that have on the yield of chlorine? He said, if I increase pressure, the reaction goes to the side with less number of moles. So in this case, it would go to the side with less moles, which is forward, because going forward gives 4 moles, going backward would give 5. So if it goes forward, then I will have more yield of chlorine. But remember that Kp is not affected by pressure. It will be affected only by change in temperature. Okay, then he says, what will happen if I increase the temperature? Again, I want what is the effect on the yield of chlorine and what is the effect on Kp? Well, if I increase temperature, remember that the reaction will go to the side that is endothermic. Endothermic here is backward, because he's saying that the forward is exo. So this means that if I increase temperature, it goes backward. And if it goes backward, that means it will give less yield of chlorine and the equilibrium constant will be less. Use of catalyst. Remember that when we use catalyst, it speeds up both forward and backward reaction. So there is no effect on the point of equilibrium. So the concentration of product and equilibrium constant remains unchanged. You have to remember that when we write the expression for Kp, we do not include any solids. So for a reaction that has solids, we totally ignore the solids. So for this reaction, the Kp is just partial pressure of CO2. The Kc for this equation would be just concentration of Ag plus times concentration of Cl minus. Solids are not included. So let's take a look at this question. Silver oxide decomposes on heating. What is the expression for Kp? Again, writing Kp, please do not include any solids. So that would be just the partial pressure of oxygen to the power half. Everything else is solid. Again, he's saying 52.6% of molecules in the gas mixture are carbon monoxide. What is the partial pressure of carbon dioxide? Well, when we write the equation, we don't include solids in the Kp. So if he says that 52.6% of the molecules in the gas are carbon monoxide, then the rest of the 100% is the carbon dioxide, and the partial pressure of CO2 is the mole fraction of that. So that is 47.4 over the total. So that is 0.474, and that gives you the partial pressure of the CO2. The equation for precipitation of this is shown. What are the units? Again, I want to write Kc. We do not include solids. So the Kc for this reaction is just 1 over the reactants. And then you put in the units. Remember, each concentration is mole per decimeter cubed. If it is to the power 2, that is mole to the power 2, decimeter to the power 6. And that means my resulting units are decimeter to the power 9, mole to the power minus 3. And then this question says calcium carbonate decomposes when heated. The equilibrium constant for this reaction is Kc is concentration of CO2, and that's it. Concentrations of calcium carbonate and calcium oxide are not included. Now, why are they not included? Because being solids, they are regarded as constant. So it is as if they're not changing. The reaction between solid copper and aqueous silver nitrate is this. What are the units? Again, in order to write the expression for the equilibrium constant, you need to exclude any solids. So it's just concentration of copper to the power, copper 2 plus to the power 1 over the concentration of Ag plus to the power 2. Put in the units, and this comes out to be the unit. Remember, when we were talking about entropy, we said delta S total is equal to R ln K. So remember that the equilibrium constant will always increase if the delta S total of the reaction increases, or the total entropy change of the reaction increases. So the question says the equilibrium constant for reaction always increases. When there is an increase in what? We said always when there is an increase in the delta S total. Remember that the equilibrium constant increases with temperature only when the reaction is endothermic. If we increase temperature, the forward reaction is endothermic, then the Kc will increase. But he's saying which one will always increase. We said delta S total is R ln K. So the delta S total, if it increases, the K will always increase. Okay, let's learn to write what we call the ice chart. This means we have number of moles initially changing and then forming at equilibrium. So if he says a chemist investigating this reaction started with 5 moles of N2O4 and allowed the system to reach equilibrium, that means initially I have 5 moles of N2O4 and nothing of the NO2. Then he says 2 moles of NO2 forms. Now, remember that in any equilibrium reaction, what is happening during formation of equilibrium? Part of the N2O4 breaks away to form NO2. Now, remember that how much breaks away, it has to do with the coefficient. So I have N2O4 has a coefficient of 1. So I will remove from the initial 5, I will remove minus x. But how much of NO2 will I form? I will form 2x, because 1 mole of N2O4 forms 2 moles of NO2. Now that means that at equilibrium, I am left with what? I'm left with the rest of the 5, so 5 minus x, and I'm left with the 2x that is formed for the NO2. Now he's saying that at the end 2 moles of NO2 form, and that means the 2x that I said should form is actually 2 moles. So what is x? That means x is 1. And that means that at equilibrium, I am left with 4 moles of N2O4 and 2 moles of NO2. And that means that the amount of N2O4 at equilibrium is 4 moles. Now, this kind of analysis we call the ice chart. Initially, what happens? What is the change? And at equilibrium, what do we have? Are we following? Let's try again. Another question says, when 0.1 mole of hydrogen and 0.1 mole of iodine were allowed to react according to the equation. So he's starting with this equation and he's saying initially I'm starting with 0.1 mole of hydrogen and 0.1 mole of iodine and none of the HR. Then 30% of the hydrogen was found to have been converted at equilibrium. Now, I know that what should change, I should lose X moles from hydrogen, lose X moles from iodine to form 2X of HR. And that means that what is left of hydrogen is the rest of the 0.1 minus X, iodine 0.1 minus X, and I form 2X of the HI. But then he said 30% of the hydrogen was converted, and that means the X that I removed from hydrogen, I removed 30% of the 0.1. So X is 30% of 0.1, so X is 0.03, and that means that at equilibrium, I am left with how much hydrogen? The rest of the 0.1, 0.1 minus 0.03, so that is 0.07. Iodine is the same, and I'm forming 2X, so that is 2 times 0.03, so that is 0.06. Another question, a flask containing a mixture of 0.2 mole of ethanoic acid and 0.15 mole of ethanol was left at this temperature in presence of a catalyst, and he gives me the equation. The ethanoic acid present in the equilibrium required 34.8 centimeter cubed of a 2.5 mole per decimeter cubed solution of sodium hydroxide for complete neutralization. Calculate the value of the equilibrium constant Kc for this reaction. So we have ethanoic plus ethanol to give ethyl ethanoate plus water. And I want to know how much ethanoic acid I'm left with at equilibrium. He said he took the ethanoic acid and he titrated it with sodium hydroxide. So ethanoic acid with sodium hydroxide, I can get the number of moles of sodium hydroxide that he used, concentration times volume. And from the equation with sodium hydroxide, it's a 1-to-1 ratio. So the number of moles of ethanoic acid is at the end, at the equilibrium point, is 0.087. So in this reaction, initially I'm starting with 0.2 mole of ethanoic acid, 0.15 mole of the ethanol, and none of the others. Now, what happens is X moles will dissociate from the ethanoic acid, X moles will dissociate from the ethanol to form X moles of the ester plus X moles of water. Now, he's saying that at equilibrium, what is left? We found that what is left of the ethanoic acid is 0.087. That means 0.2 minus X is 0.087. And that means if I calculate what is X, it comes out to be 0.113. And that means that at equilibrium, I have this value for ethanoic acid, this value for ethanol, X of each of the products, and I can see from the expression for Kc, concentration of products over concentration of reactants, I put in, remember that the Kc is a value of concentrations not number of moles. But then each of these concentrations is the number of moles over the total concentration is number of moles over volume. So the volume cancels up and down. So actually, I can use the number of moles instead of concentration only because the volumes cancel. So the Kc in this case will be a certain value, 3.97. There are no units because the units will cancel up and down. So that's the value for Kc. Okay, another question. Ethanol may be manufactured by the hydration of ethene. In a laboratory investigation of this reaction, he started with 1 mole of ethene and 1 mole of steam at equilibrium when the total pressure of the system was 50.45 mole of ethanol had formed. Give the expression for Kp. So first of all, Kp is the partial pressure of ethanol over the partial pressure of the reactant, C2H4 times partial pressure of water. And he's saying calculate the equilibrium constant Kp. We have this reaction. He told me that initially I have 1 mole of reactants, none of the ethanol. And I should know that the change that happens is minus X from the C2H4, minus X from the water, and an X moles of ethanol is formed. And that means at equilibrium, he is saying that at equilibrium, I have 0.55 mole of C2H4, 0.55 mole of water, because 0.45 mole of ethanol were formed. Remember, he gives me the value of X. X of ethanol is formed, and he said X is 0.45, so I calculate the number of moles of each. At equilibrium, the partial pressure of each one. Remember that he wants Kp. The partial pressure of each one is the number of moles of that over the total number of moles times the total pressure. He tells me that the total pressure is 50. And if I have 0.55 and 0.55 and 0.45, then the total number of moles is 1.55. So I can get the partial pressure of each one and use that value to get the value for Kp, which is partial pressure of ethanol over the partial pressure of the reactants multiplied by each other. So I get Kp is 0.0461. Is that clear? I hope that was clear. I hope that helped you to understand the chapter, and thank you for listening.